Good morning. Today we are going to discuss about the unit 5, the application ICs. So in this we are going to see the concept called regulators. So the concept, the voltage regulator. The function of this voltage regulator is to provide a stable DC current. So this stable DC current is used for powering the other electronic circuits, and it's mainly used to stabilize the load current. In this conditions, the voltage regulator, it is classified into two types. One is series regulator, the other one is switching regulator. Comes to that series regulator. So this series regulator, it uses a power transistor. So this power transistor, I will show it in this diagram. So this power transistor is connected in series between your unregulated power supply V in and to that regulator power supply V naught. So in this is like a V naught as the regulated. Once after doing this process, we will be getting a regulated DC output that is connected to the load. So it is placed in between your unregulated and the regulated, that is in between your V in and the V naught voltage. So this is connected in series between those two regulations. So here the output voltage is controlled by the continuous voltage drop. So this continuous voltage drop taking place across this load. So this makes my series parallel resistors, series pass transistors. So the thing again I am repeating, the output voltage is controlled V naught. So this output voltage V naught is controlled by the continuous voltage drop taking place across the series pass transistor. So since this transistor, usually we have studied the transistor works in the three regions. One is the cutoff region, the saturation region and the non-saturation region. So we call this transistor, we can work in the active region and the linear region. So this we call it as a linear regulator. So this series regulator we can call it as a linear regulator. So this linear regulator is again classified into a fixed and the variable voltage regulator. So here the fixed is nothing but a fixed voltage is given to that circuit, like a 5 volt or 12 volt, 8 volt, whatever may be the voltage, that should be a fixed one. That we call it as a fixed output voltage regulator. Whereas that variable, every time the voltage may get varied. So this we call it as a variable output voltage regulator. So in this condition, this fixed and the variable have included in both the positive and the negative voltages. For example, we can use this linear voltage regulators in the series of 78XX and 79XX. So this 78XX will represent only for the positive voltage regulators, and the 79XX is then for the negative voltage regulators. The later we are going to see what was the 78XX series and the 79XX series. So these are the points comes under that series regulator. As I mentioned, the power transistor is connected in series with your unregulated DC input voltage to that regulated DC load. So here the output voltage of this V naught is controlled by continuously by varying the voltages in the across this transistor, and this transistor can conduct either in the active region or in this linear region. These regions are called as a linear regulators. So this linear regulators is of two types. One is the fixed output voltage and the variable output voltage. So here the variable output voltage that can be adjusted every time, whereas the fixed output voltage where the voltages were the fixed voltages. So here it may have both the positive voltages and the negative voltages. For this linear regulator, we have a 78XX as the positive one and 79XX as the negative voltage regulators. So this, and we have one more ICs called I'll see as 723 as a voltage regulators. So coming to that switching. So in that name, the switching means it can either switch on or off. So this is like a switching regulator. It acts as a switch and it has two conditions, either on or off condition. So it operates with the power transistor with a high frequency on off switch and the power transistor. So here it works continuously, whereas in case of the switching regulator, the power transistor does not conduct continuously. It may be either on or off. In that on condition, how the voltage will be, and in the off condition, how the voltages will be. So these are the switching condition. We have both on and off conditions, and it improves the efficiency. It improves the efficiency. Usually we call this, write it in the notation of eta. So this efficiency improves with the help of the switching regulator when compared to the series regulator. So first we are going to look into that series regulator, later we move on to that switching regulator. So this series regulator, coming to that series op-amp regulator, here we have that input voltage as VDC. It is connected with the resistance R0 and the voltage is Vin. It is given to the transistor Q1 as the collector terminal. That emitter terminal, we have taken an output, and we have a load resistance, and we have a divider networks like R1 and R2. That part alone is the in between R1 and R2, the terminal is given to that inverting terminal of your amplifier, whereas that non-inverting terminal is connected to that diode with the voltage as reference voltage, that other terminal to be grounded. And this feedback network, we have produced this output voltage beta into V0. So this is the outline of the circuit diagram. So one thing we have to know, where we get the voltage regulator. So in case of the Zener diode, the reverse bias condition, once you keep on varying your voltage, it produces the maximum current as a stable one. So in that condition, I have mentioned earlier, this voltage regulator is providing a stable DC voltage. It provides a stable DC voltage and it gets powered by the other electronic circuits. That's the main definition, circuits. So coming to this, in this circuit we have four parts of this main part of this op-amp regulator. So one thing, we have a reference voltage, that is your V reference voltage. Then we have error amplifier. So error amplifier, this like a comparator circuit, we compare the voltages, two different voltages. The other one, we have a series pass transistor. And the fourth one we have is the feedback network. So in this, the power transistor Q1, as I said earlier, the power transistor Q1 is in series with the unregulated DC voltage Vin and the regulated DC voltage V0. So it observes the difference in the voltages Vin and V0, and therefore the difference in these two voltages have any fluctuations in the output voltage occurs. Then the transistor Q1 is also connected as an emitter follower, and therefore it provides a sufficient current gain to drive this load resistor, so that the output voltage is sampled, and then output voltage V0 is sampled by the resistors R1 and R2. It's like a divider and it's fed back to that input terminal of that error amplifier circuit. This is like the inverting input terminal of the error amplifier. So this error amplifier samples the voltages. So here we have applied an output voltage that is given to this inverting terminal, that is to be sampled, that is compared with the reference voltage, that is the output of the error amplifier. It's a V0 dash which is used to drive the transistor, series pass transistor Q1. So in this, the output of the error amplifier which drives the transistor Q1, the output voltage V0 dash, that due to this makes there is a change in the load current. So this load current gets changed IL. So one thing, if I am going to make this V0 dash is connected to the base and it is driving this V0 transistor, here we can call it as an emitter follower circuit. So in this emitter follower circuit, in that beta condition, feedback condition, I can mention the relation beta as the opposite resistor by the sum of resistor R1 plus R2. And this emitter follower circuit, we have studied that in the case of op-amp as the voltage follower circuit. So it is relevant to this voltage follower circuit. In that condition, I am making my V0 output voltage is equal to V0 dash, or V0 dash is equal to V0. So in that condition, if I am going to increase my V0, so in this condition, if V0 is increased, ultimately your V0 dash gets increased. This V0 dash which drives this V0. So if V0 dash is increased, ultimately this V0 increases. That's the condition if I am going to make a stable DC voltage. So in that condition, I am going to make this V0 as nullified. That is, you are going to make a nullified one and you are going to reduce the output voltage to a DC voltage level. Okay. So here we have the four components: voltage reference, error amplifier, series, feedback. They already I have mentioned the Q1 transistor is connected between the unregulated and the V voltages. In that condition, this transistor which is controlled by the voltages, it drives the sufficient current gain and to drives the load current, and the V0 is sampled by the resistors R1 and R2 divider and fed back to that terminal as the inverting input. This V reference is sampled a reference with compared with this voltage and it produces the V0 dash, that V0 dash which helps in driving the series pass transistors. This condition, it acts as an emitter follower, nothing but an voltage follower. In this V0 dash will this V0. In this condition, an error occurred is very less. Ultimately the output voltage produces a low voltage. So to make that increase in V0, if I am going to increase in V0, it's nullified, and similarly the reduction in the output voltage also gets reduced, that is to be regulated. So the next topic is the IC voltage regulator. So in that condition, the IC voltage regulator. So the next topic is IC voltage regulator. So usually the IC voltage regulator, we have to make a voltage as a stabilized one. For example, that 78XX, this voltage may be a 7805 and this voltage produces a plus 5 volt, because I have mentioned it's a positive voltage. So it produces a plus 5 volt to be processed. That will be a constant one for this entire process. So in this voltage regulator, it will be in a IC format. So this should be in a complete an IC format. So in that, in completion, that is we are making all those components, that is to be complete circuits on a monolithic IC. This we have discussed in that unit 1 as the monolithic IC and the hybrid. We generally know the definition of IC. We are integrating the resistors, not the inductors, it's the capacitors and the transistors, diodes to be incorporated in the ICs. So here that IC voltage regulator, we have that incorporating a complete circuit in a single monolithic silicon chip. So here this IC voltage regulator, why we prefer this IT voltage regulator? Instead of we are making a circuit, we are incorporating it's a single silicon chip. It is like a batch production. So yes, the cost wise it is low cost and it is highly reliable. And the major point is reduction in size. And the fourth one is the excellent performance. So this we have both fixed and the variable voltage regulators. Now we are going to see the fixed voltage series regulator. So here in that fixed voltage series regulator we have three terminals. One is the input terminal, the other one is the output terminal, and the other one is the ground terminal. So in that input side we are giving an unregulated supply V in, and we should get a regulated output as the V naught. So the third terminal as the ground terminal, that is to be grounded. So in between your input terminal and the ground terminal we have an input capacitor Ci with a value of 0.33 microfarad, and its material coated by this capacitor is the ceramic material are used. This ceramic material is connected, the capacitor Ci with a 0.335 microfarad with the ceramic material is used to connect the between the input terminal and the ground terminal. It cancels the inductive effects. That too, where the long distribution leads, we have the inductive effects that to be cancelled. So in case of the other condition, that C naught, which is made up of the tantalum material, which is connected between the output and the ground terminal, it is connected. So this output capacitor C naught is used to improve the transient response. So this is the main thing. The fixed voltage regulator is a 3-terminal device with the 78XX series. If it is in case of your 7805 or 06 or 15 volt, 12 volt any voltages, this unregulated voltage is to be processed to produce a regulated output as V naught. So that we have used the input capacitor and the output capacitor. The input capacitor is made of ceramic and the output capacitor is made of tantalum. So now I have writing that 78XX, as I mentioned, it's a positive voltage regulator, and this positive voltage regulator is a 3-terminal device. We have seen input, output and the ground terminal, and it's a positive fixed voltage. As I mentioned, we have positive fixed voltage regulator. We have the voltages like 5 volt, 6 volt, 8 volt, 12 volt, 15 volt, even 24 volt. Like that we can give the positive voltages. In case of my 78XX is again a 3 volt, 79XX is like a negative voltage, and it has the output fixed. This is like a 3-terminal negative voltage. It's again a fixed voltage, and this ranges is like minus 2 volt and minus 5.2 volt. So this XX, what this XX represents the output voltage. If I can mention 7815. So in that condition my 15 volt will be the output volt. So here this ICs are made up of 2 packages. So 2 types of packages. One is the metal package and the ceramic, so like plastic package. So in case of the op-amp discussion, we have made a metal package, plastic package and the ceramic package. So these type of packages, 2 packages like metal and the plastic packages are to be used. And the standard representation of these 3 is capacitor C0 and C0 is connected between the output and ground. Here it is connected between the input and ground. That's the fixed voltage regulator. So here that IC LM100, we can make this regulators with LM100, LM200, like LM300 series regulators. So those every ICs may vary with the temperature ranges. So in this LM100, this LM100 is defined for minus 55 degrees centigrades to 125 degrees centigrades. It's like a positive. Mine starts with minus 55 degrees centigrades to plus 125 degrees centigrades, whereas LM200 starts with minus 25 degrees centigrades to 85 degrees centigrades. Then again, for LM300 series, it starts with 0 degrees centigrades to 70 degrees centigrades. It's like both we have negative range and the positive range for your LM100 and 200 series, whereas of LM300 it starts with 0 degrees centigrades to 70 degrees centigrades. Then coming to the characteristics of that fixed voltage series regulators. The thing we have mentioned that it's like a 3-terminal devices, so that the characteristics are to be classified in 4 points. So the classified, as I mentioned, the output voltage should be a fixed voltage. That's the main thing to be included, is like fixed voltage regulator. So here the fixed voltage regulator, as I mentioned, 78XX, the 7815 volt, it represents the 15 voltage regulators. And the second point, which is greater than or equal to, so here the modulus of your input voltage should be greater than or equal to V0 plus modulus of your V0 is nothing but it defines a positive voltage regulator plus 2 volt. So in this condition, the output voltage, example, if I am choosing my input voltage V0 voltage as the 5 volt, my V in voltage will be a 7 volt. It will be like 2 voltages more than the value of your input voltage. Your input voltage will be greater than your output voltage with 2 volt. The third one, so here we are going to find the maximum current. So this maximum current, which is derived from that load current, we have to produce a 0 to the maximum current rating. So once you produce the maximum current, so you have to provide with the heat sink. So the concept of this heat sink, you have to make cool your IC. So once you are giving a maximum current, ultimately your IC gets heated. So for that concept, we have used a thermal shutdown. So shutdown in the sense, thermal, we understand it's a heat. When we get an excess heat, if it is beyond the limit, the IC should make automatically off. So for that, this thermal shutdown, we have an inbuilt temperature sensor. So then only we can make our ICs to make cool. So this temperature sensor, every temperature sensor has some particular range of that temperature. As I mentioned, that LM100, it starts in the range of minus 55 degrees centigrades to 125 degrees centigrades. Whereas in the case of this temperature sensor, it can withstand maximum of 125 degrees centigrades to 150 degrees centigrades. So if it gets too hot, then it automatically your IC turns off. So next we are going to see few definitions. One is line regulation, or I call it as input regulation. The another definition we call it as load regulation, and the third one we call it as ripple regulation. The line regulation, or we call it as an input regulation. So here it is defined as the percentage change in the output voltage to that input voltage. So everywhere it's like a percentage change in the output voltage to that input voltage. This is like the unregulated output voltage as the V in, and the regulated output voltage as the output voltage as V0. So everything it should be measured in terms of the millivolt. In that condition, that 7805, this line regulation, it can withstand up to this 3 millivolt line regulations. It's like a line regulation. For this 7805, it has a maximum voltage as 3 millivolt. Coming to that load regulation. So load regulation, here we can define, it is defined as the change in the output voltage. So it's change in the output voltage to the change in the load current. So here the load for this 7805, it should be, again it should be measured in that millivolt, expressed in the millivolt, and this can withstand a 15 millivolt. So here we have the current ratings too, because the output voltage and the load current. So we don't get the output, it can withstand the maximum as the 15 volt, and the current rating of this is nothing but your I naught, output current value varies from 1.5 5 milliamps, 5 milliamps to 1.5 amps. So the rating of this load current will be like a 5 milliamp voltage to the 1.5 amps, and it should have a 15 millivolt. When compared to line regulation, it's 3 millivolt. When compared to this load regulation, the 7805 should have a 15 millivolt voltages. Then ripple regulation. So in this ripple regulation, so we have studied what is ripples. It's like a noises. So the regulation, as usual, we helping the whole function of this voltage regulator is to stabilize our DC voltage. In case if there is any excess noises, those things are to be removed. That's the definition in this ripple regulation. So here the IC regulator not only keeps the voltage constant, and it reduces the ripples, Okay, so here we are going to consider for this 7805. So these regulations are to be measured in case of 7 decibels, and this decibel value, it stands at 78 decibels. So the next topic is the current source. So coming to this current source topic, here we are using a fixed voltage as a current source regulator. So in this current source regulator, we have wired a 7805 voltage is wired between that unregulated and the regulated output voltage. So here we can see, similar to this unregulated input voltage, like fixed voltage series regulator, here we have input terminal, output terminal, and the ground terminal, the same input, output, and the ground terminal. Here we have connected that capacitor input, and it is to be grounded, whereas the second and the third terminal is connected with the IR current flows and the resistor. Here the IQ is nothing but your quiescent current, and your IL is nothing but your load current. So here we have the output voltage, and in between we have two voltages like VR and the VL, with the 5 ohm resistor and the 10 ohm and the 10 watts or load resistor to be connected. As I mentioned, my Vin voltage will be greater than V0 with the 2 voltage. So here there may be the terminal input and the output terminal 1, 2. We have Vin minus V0 equal to 2 volt. So you can see that load current value can give that addition of your quiescent current and the resistor current flows is IR. So I can write my expression IL is equal to IQ and IR. So as I mentioned, in the fixed voltage, that's the current source concept. So I can write my expression IL load current as IQ is the quiescent current plus IR. So this IR is taken across the voltage VR and the flows across the resistance as R1. So this IQ is the quiescent current. This IQ quiescent current for this 7805, we can mention the value as 4.2 milliamps for this IC 7805. It's a 5 volt regulator. So in that condition, I can vary my IL. IL is defined as 1 amps. So this 1 amp VR by R1, which is given, is approximately equal to 1 amp. So in that condition I can say my IQ value is very less when compared to that load current. Of course, this IQ current, so by reframing that we can say it's as VR is equal to 5 volt is given and it is placed between the terminal as 2 and 3 terminal. So in that condition I am going to find that load resistor. So you know that VR by R gives 1 amps. So VR as 5 volt, thus 1 amps it gives a 5 ohms. By placing 5 volt by 1 amps, it gives a 5 and 1, it is 5. It's like 5, it's voltage, and it's ampere in terms of ohms. So this R is equal to 5 ohms is derived. So in this we are choosing R is equal to 5 ohm to deliver 1 amp current to a load of 10 ohms. So the next topic is the fixed voltage regulator as a adjustable one. So in case of the current source, we have used a fixed voltage. That fixed voltage value for this 7805, the quiescent current is 4.2 milliamps. Here I can classify that load, not classifying, it's like a total current of your load is derived from your quiescent and the current flow through the resistor. So in case of your fixed resistor is used as a adjustable resistor. So if in the laboratory one needs to change the voltage, so in that condition a fixed voltage resistor is used as the adjustable resistor. So in this concept we are going to see a diagram. See here again, this is an operation, it's a IC voltage regulator. Its input, output pin, ground pin. We have given an input voltage. We are going to get a DC regulated output voltage. Here we are going to concentrate more on your second and third pin, and this fixed regulator means the ground pins are to be kept floating. So in this every time it's to be grounded with the floating terminals. That output and the second and third pin is connected across this IR1 and the resistor. Here we have the voltage as VR, and here in this resistor R2 we call it as V pot, and the current flow IQ. Here the current flow is IR1, and the capacitor between your 2 and 3, here it is grounded, it is like a 0.1 microfarad. Initially I have mentioned that input side it's made up of ceramic and the output it's like 0.1 microfarad. So it's like a floating point. If one mainly it is used in the laboratory purpose to vary the voltage. That's the main ultimate aim of this adjustable regulator concept. So here I am going to take that voltage. So the voltage is sum of your VR and V potentiometer. So I can write the expression VR as V0 plus V V0 as VR plus V pot. So a potentiometer is used to adjust the voltages. So I can write that VR as such, and the potentiometer, here I can have the two currents. That current we call it as IQ, and the potentiometer is the sum of your IQ and the IR1 current, and with the resistor R2. So I can make the expression VR plus IQ R2. Separately I can write IQ R2 plus IR1 R2. Again we can write VR plus IQ R2 plus IR1 is nothing but the voltage across this resistor VR and the R1. So V is equal to IR, I is equal to V by R, right? So I can write VR divided by R1 into R2. Now in this expression I am going to take the VR as common. So 1 plus R2 by R1, and we have a quiescent current is multiplied with the R2 resistance. If IQ is minimized, so the condition quiescent current is minimized by varying a small value of R2. For example, if I multiplied with 0.001, my current IQ is 1, that it's multiplied, it gets its 0.0001. So ultimately this IQ is minimized by reducing the values of the R2. So this fixed voltage used as the adjustable resistor, here the L, it's like a variable one. So here I can use both positive and negative voltage regulators. The series LM117, LM217, 317. These three is used for the positive regulators, whereas the LM137, 237 and 337 is for negative voltage regulators. So these are like a special regulators are used in the fixed voltage regulator used as adjustable special voltage regulators.